of policies enabling pilot deployments and projects and real-world testing, Michigan is taking emerging mobility and electrification technologies from concept to deployment, from mind to market. The future of technology is accessible, sustainable, and equitable, and it's being built right here in Michigan.
Thank you, Sachin. So our first speaker is going to be Eric Schreffler. He's the Vice President of Market Development for the Michigan Economic Development Corporation. In his role, he and his team work to support the state's major industry clusters, identify new market opportunities, assess emerging technologies, support international business development, and work with various stakeholders to establish economic development opportunities for the state. Eric, you can come on stage. I'm sure Eric has been able to log back in. So if he does, we'll bring him on stage sometime during the program. So why don't we move on to our first speaker? I'm sure when Eric joins us, we'll give him his time. And that's Alice Swallow, who's our keynote speaker from the Ford Motor Company. Alice is a senior innovation research engineer within the UK innovation team at Ford Motor Company. Looked predominantly at lightweighting for commercial vehicles. She started at Ford as a hire apprentice in engineering, has worked in various departments from gasoline calibration to chassis engineering. Her remit with the innovation research team is to project manage studies on lightweighting technologies and applications and design with mass production capability. She has 2 patents pending on e-motor and tooling for multiple material selections. She won the Autocar Magazine Great British Woman Apprentice of the Year in 2018, was runner-up in the IMechE Apprentice of the Year 2018. She has a first-class honors degree from the University of Greenwich in the UK. She's a member of SAE, IKE, and the secretary for the IMechE in the South Essex area. Alice, look forward to your talk. Can you join us with your microphone and your camera?
For the introduction. Hopefully you can all hear me okay.
Thanks, Alice.
Perfect, thank you. So I'm just going to talk to you a little bit today about our chassis project, which is a research and development project on using composites and metallics in a hybrid way to enforce the right material in the right place. For suspension system components, so looking at structural components as our strategy is that if you can apply this technology on structural components and the most complex components, then there's no reason why we can't apply this technology in other aspects of the vehicle. So a bit of an introduction on the project scope. So as Dale mentioned, we look predominantly at commercial vehicles in the UK. So even more so, it's important to lightweight our vehicle and our components to ensure that we can increase the payload for our customers. So really crucial for lightweighting there, as well as obviously other performance targets. So the project scope, obviously with commercial vehicle, we're looking at mass production capability, very high mass production capability, which has given a project requirement of a cycle time of under 5 minutes to manufacture each component. We're also looking at a volume of 500,000 vehicles per year. So that's the kind of mass volume that we're looking at. Some key targets that we've looked at for this research and development project, in order to ensure that there is adoption of these technologies into program, we set a quite high cost target of $9 per kilo of weight save so that we can have the most innovative designs for the components that were chosen, as well as obviously the cycle time and a weight reduction of 40% over the 3 components. There's obviously a lot of technical challenges with this. So as I mentioned, they're all structural components looking at the suspension. So it's really important to look at the strength and stiffness and design verification. A lot of these parts, the strength and stiffness will actually determine the vehicle dynamics. So obviously we don't want to change our vehicle dynamics DNA that our customers are used to. The three suspension structural components that we're looking at are the front subframe on the left, the front lower control arm in the middle, and the rear dead beam at the end, which is just the rear non-driven axle. We have the steel components on the top and our hybrid designs at the bottom, which I'll go into more detail in later slides. So another great aspect of using the right material in the right place and using composite materials and adhesives in a way in the design that we can actually reduce the part count within these components. This is a great way to ensure that it can be easily integrated and assembled. Obviously, that reduces a lot of complexity. It reduces a lot of opportunity for error and therefore improves quality. And across the three components that we looked at, we actually had a 56% reduction in parts. So that was another benefit of the project there. So looking specifically at the front subframe, so there's an estimated of around 38% weight reduction for this part. We're using the right materials in the right place here by using different materials. We're using aluminium as well as composite materials. So the side rails on the left hand side of that image there, so they'll be produced out of a high pressure die cast aluminium material. However, for the prototypes that we're currently at the stage of assembling these prototype parts for the project, we're actually machining these out of solid billet. Just for your reference, the billets are currently 132 kilos at the moment, and once machining is complete, these side rails are 2.82 kilograms. So a lot of swarf created in that process. Don't worry, we're recycling them and keen on sustainability. But just to show you the complexity and the amount of pockets that have been created on that design by Gestamp to ensure that we can have the ultimate weight saving and lightweighting on these parts. We also use carbon SMC. So on that front rib section there, you can see the carbon SMC. We also have carbon prepreg upper and lower panels, and an aluminium extrusion bar on that front edge there as well. We also have the steel steering bobbins and transmission bobbins taken from the predecessor part. So it really does apply the right material in the right place, looking at the CAE analysis at the load pass to ensure that we have the right material and the optimized layouts for the optimal cost and weight saving scenario. And designed as well for adhesive bonding in mind, so ensuring that there is enough gaps for on the edges of each subcomponent to ensure that there is enough adequate spacing for the adhesive as well. So looking a little bit at the CAE analysis for the front subframe. So as I mentioned previously, a lot of these parts are driven by their stiffness or strength targets, certainly to ensure that the vehicle dynamics is similar to the predecessor vehicle, to ensure that ride and handling is similar for our customers. So it was really crucial for us that we had comparable stiffness targets, which was done by our partner Gestamp on the project. Our next part, the front lower control arm, estimated around 29% weight reduction. So this uses also the hybrid material and right material in the right place, with looking at a steel puck for integration into the wheel and into the body, as well as our original bushes as well, for ease of assembly. But we're looking at a PA12 long glass fiber core using overmolding technology, and PA12 long carbon fiber shell, also overmolding over the core. Again, this was looking at the load pass and the connection to the system by using the steel 0.6 puck, and then the hybrid of materials, looking at for the rest of the part. This was designed predominantly with overmolding in mind to ensure that we could achieve the quick cycle time. And there's also a patent pending on this design for Gestamp, who designed this part. So again, the CAE analysis for the front lower control arm. Obviously, front lower control arm is a very key component for strength and stiffness. Strength being the key design driver. We usually think it's optimal for the tire and the wheel to be attached to the vehicle. So it's really important that that these parts meet these strength and buckling requirements. With a x-axis buckling load of over 42 kilonewtons and y-axis over 50 kilonewtons. So there's obviously a lot of forces and low pass going through these parts. So it's really crucial that we meet those. All CAE, all targets have been met through CAE, and we're currently in the stage of making these prototype parts ready for physical testing. And the last component, the rear dead beam. So this is using a process called pultrusion. So again, this is a continuous process, which is great for hitting our mass production targets. We can get a cycle time of well below the 5 minutes. And it also reducing the number of components in the assembly by 8 components per assembly. So we have aluminium extruded parts for the jounce bumper plates and for the hub mount attachments, so attaching those to the wheel. So they're 2 separate parts, and we also have some dampener bracket attachments as well. But other than that, we just have the rear dead beam, just 2 pultruded composite beams, and they're made of a hybrid materials also. So we're looking at a unidirectional glass toe with as the main material of the beam, with a triax carbon material as the sort of inner core for the structure of the beam, and a woven carbon and tapes on the outside of the beam. So again, the CAE analysis for the rear dead beam, as it's an identical part from it's sort of mirrored from left to right. You only need to analyze the right one side of the part. And again, obviously, this is a very structural component, so driven by stiffness, strength, and durability. Looking at strength and our road load data with our max load being 56 kilonewtons as our key design target there. So again, with the CAE analysis, we have, excuse me, all targets have been met. With physical testing of some of the subcomponents have already been conducted, which has correlated well with the CAE analysis that's already been conducted, with plans for the components being currently assembled, with full assembly rig testing in the next few months, and then full vehicle testing after that. Looking a little bit about life cycle analysis and also the CO2 saving of composite parts. Obviously, it's really important to look at the overall sustainability and end of life requirements for these parts. So on the right hand side, we have some life cycle analysis, sort of CO2 saving plots, looking at the difference between the steel predecessor parts and these hybrid composite parts. So looking at the front subframe, the current part over the space of only 5 years does give the CO2 saving back for that part. So we've got 3.35 years for CO2 output reduction there of the CO2. But obviously, when you look at the life cycle of a vehicle, it's usually much greater than 5 years. So that's just showing on such a small scale when the CO2 saving can take place. Similarly, for the front lower control arm, only 1.3 years for break even for CO2, and less than a year for the dead beam, so 0.65 years. We actually get a break even for the CO2 output. So obviously over time, this will be reducing CO2 and looking at sort of carbon negative for those parts. So overall, looking at the weight saving for all three components, we had a weight reduction of 44%, so over the 40% weight reduction that had been planned. So that our project target was around 25 kilos, and we've saved 30.6 kilos by using a hybrid material in the right place approach. And some conclusions for where we are currently in the project. So we have achieved our sub 5-minute cycle time by utilising processes such as compression moulding, pultrusion and overmoulding. So a lot of these processes has allowed us to ensure that we meet that cycle time requirement for mass production, which can ensure that the full annual volume of vehicles are achievable off a single tool. We've achieved a 44% weight reduction, so over the 40% compared to the original scope of the design, as well as the additional benefit of 56% reduction in the number of parts within assemblies to reduce complexity and improve quality of our design. There's been lots of innovative CAE optimization and topology that's been developed by our partner Gestamp. We've also had manufacturing simulations which can predict test conditions. So we found that with the start of our physical testing of some of the subcomponents, this has correlated really well to the CAE targets and CAE analysis that's already been conducted. All components that have been designed have met those CAE targets, and because of the correlation, we're really confident that those components will meet the physical testing. But we'll confirm when obviously full assemblies have been produced and tested, with vehicle testing starting in a couple of months' time. And we believe that the cost per kilo weight save target has aligned really well, and we believe that we've fully met those cost targets that were in place for these components also. So thank you very much. I think there's time for questions at the end, but also any other questions, please feel free to contact me on LinkedIn. Also, thank you to and acknowledgements to the rest of the team as well. This hasn't just been a Ford team. This has been a lot of work has been done by our partners Gestamp, University of Nottingham and NCC. So obviously their expertise has been greatly appreciated on the project. Thank you.
Thank you, Alice. Yes, we do have a couple of minutes for questions, and then if there's some time left over at the end, we can cover those as well. I think there are a couple of questions that specifically related, in a multi-material structure like this, with both metal and carbon fiber. What did you do to isolate the metal components to prevent corrosion?
Yeah, of course, that's a really good question. Obviously, when you've got metallics and especially carbon fiber, there is obviously that concern with galvanic corrosion. So a lot of the time we've ensured that there's been a thick enough adhesive gap, and actually using the adhesive as a barrier for corrosion. But again, we want to do some salt spray testing to really sort of test that theory out.
Okay. One other question, and I think this is kind of top of mind lately with circular economy being so important, is what considerations did you make for separating materials at the end of life?
Yeah, of course, that's again a really important question. So ease of disassembly is important. A lot of the joining methods that have been used in chassis is through adhesive. So that will ease disassembly in order for recycling at end of life or reuse at end of life.
Okay. Yeah. And, Eric's on, so we've got him available to make his talk. So we can't get to more questions right now, but Alice, if you could go into the chat and answer some of those while the other speakers are talking, that would be great. And then if there's still some left at the end when we have our discussion, we'll continue to cover some more.
Yeah, of course. Thank you.
Okay. Thank you very much, Alice. Okay, before we move on to our to Volkswagen and Porsche, we have Eric back. So Eric, good to see you again.
Yes, thank you, Dale. Appreciate it. And apologies, I don't know what happened before. I got kicked out of my own video, so. But
well, the video was good. It played well, and so I think it showed well too. So
perfect.
All right, we'll give you your minute and a half of fame here.
Appreciate that.
Thanks.
And again, thanks, Dale, and greetings to everyone from the state of Michigan. I do hope that the video gave you a small taste of what's possible when you're part of one of the most innovative automotive ecosystems in the world. With the electrification and automation of transportation systems, lightweighting will play an even more important role in the decade ahead. And much of the development, testing, and production of new, lighter, cleaner mobility solutions will take place here in Michigan. I invite you to learn more by joining us at our JEC virtual booth, visiting michiganbusiness.org, or contacting me directly. The Michigan Economic Development Corporation has been a proud sponsor of JEC World's automotive program for the past 5 years. It's a great opportunity to bring together leaders in advanced composites, car makers, and suppliers. And I hope that you enjoy from hearing today from all the experts, including Alice, who just was on before me, and really appreciate your participation in this important discussion. So with that, Dale, appreciate you slotting me in here, and I hope you all enjoy the rest of the program. Thanks so much.
Okay, so we'll go back to our next presentation. Our next presentation is a dual presentation from Christoph Kuhn and Dominic Kleiber. Christoph is working at the Volkswagen Group Innovation Center in Wolfsburg, Germany. He's a senior project manager. His work focuses on novel material solutions for automotive applications. He graduated with a doctorate of engineering from FAU in Erlangen in Germany, and a master in science from the University of Wisconsin-Madison in the U.S., and a master of science and bachelor of science from RWTH in Aachen, Germany. His co-presenter is Dominic Kleiber, who studied between 2014 and 2017 for a Master of Science in Mechanical Engineering and Management at the Technical University of Munich, after obtaining his Bachelor of Engineering in Mechanical Engineering at the Baden-Württemberg Cooperative State University in Stuttgart. Since 2017, he's worked as a development engineer at Porsche AG in Weissbach Body and Advanced Engineering. His PhD thesis has focused on the evaluation of functional, integrative, lightweight potentials and automotive structural concepts. Christoph and Dominique, can you join the stage?
So from our side, thank you for having us here. Chris, you can also connect and share your video if you want, so that everyone can see you as well. Thanks.
Hello.
All right.
Took a while here.
Take it away, guys. Good to see you. Thanks.
We are happy to present today the project Leomit Hybrid. The project Leomit Hybrid is a government-funded project funded by the Federal Ministry of Economic Affairs and supervised by the project sponsor TÜV Rheinland. The project is, as you can see here, based on a Porsche Boxster with a current steel aluminum design, and we had the goals to develop, manufacture, and validate a new lightweight center tunnel in a multi-material design. The goal was to achieve weight savings with approximately 20 to 24% and have at the same time only moderate lightweight costs. One of the biggest challenges at the beginning of the project was that we wanted to integrate the center tunnel before the production of the body in white. So we wanted to process it through the end process as well. So we have the validation we needed the validation for the temperature influence, the validation for all the joining technologies and different material behaviors at the different temperatures. Also, the project, such as VW, next to VW, also Schneider Form, the tool manufacturer Invent, and the Institute of Engineering Design IK from TU Braunschweig. Overview of what we have done in the project, which ends of a project. This is the overview also in the agenda for today. We started with the existing design of the Porsche Boxer, as mentioned, in aluminum steel components. Then we developed a live different materials as a new concept. We implemented this technology and created somehow a new manufacturing process for somehow mass production of this hybrid prototypes. We inserted this center tunnel into different components at Porsche, above all in the development center in Weissach, but also in the production line in Zuffenhausen. We did different tests regarding the cathodic dip painting and different crash analysis. And then there's the last step of transfer this know-how or this knowledge into new concepts for serial production. The existing, you can see here, different the body structure of the Porsche Boxer and the center tunnel assembled and disassembled, so you can already see that there are plenty of different single parts which normally have to be joined. In our concept, we just have one part, and therefore we need two tools, which I will show you on the next slide. So we rib injection and for the forming of the carbon fibers. Maybe I just disconnect my video because it says that the connection is low. So, okay, hope it works well. So we have the center exists of the glass fiber reinforced injection molding rib structure. But then we have the main part, the carbon glass and carbon fibers. The hot stamp steel insert for connection to the front of the vehicle or front of the body in white. The thread inserts for connecting all the different pipes, and load transfer elements for connecting further elements here. On the left side, you can see that we are not using just a single, like a big UD tape, of several layers with a special layup in different fiber directions. And we have the main part for overall stiffness. Then we have in brown, which you can see in the middle, further layers for the, above all, for the load transfer for front crash, and further like 90 degrees switched layers also for the front crash, because there we have different load paths. In order to keep the element together, we needed further pins here. So this is how we could evaluate and be able to integrate such a complicated part with the complicated load cases in one part. So Chris, now I hand over to you. Maybe you can show us how we've been able to manufacture such a part.
Yes, thank you. And on the next slide, you can basically see, Dominic already mentioned the core feature of this component is the fiber, or the UD fiber placed different layers that we have. You can basically see how the processing on this side looks. So basically, I mean, we're starting from unidirectional tapes, and I think some people of you have seen these tapes before, have worked maybe with these tapes before, but it's basically just like unidirectional glass or carbon fibers in these thermoplastic tapes. And then of course we can use these thermoplastic tapes and use a different process to bring up all the different layers in the complete lineup of all these different layers, which of course has the benefit that we only use the material in the direction, especially costly, for example, carbon fiber, only in the direction of the load. And for us, of course, it's very it's a great benefit to actually just use as much material as we need right in the direction where we need it. So basically, we take these different tapes and we can just put them, for example, in an automated fiber placement machine and get the specific tape layup that we want. So out of one unidirectional tape, we make those different layers. And of course, at this point, with most common automated fiber placement machines, those are almost loose, just consolidated in various locations. Then the next step after, of course, is consolidating. And so everything in this space or in this step is for really bringing all these different layers together and basically getting out air and consolidating one plate that we can actually use easily during handling and during manufacturing. So basically everything you see until the consolidated plate happens somewhere else. And then basically in the next step during our processing, when we actually overmold the material with plastic, and we basically bring in all these different components of metal, injection molded plastic, and the layup here that happens in the production process. Of course, due to timing, we weren't able to show our production process. We actually have a cool video, but this would totally go against the time constraints here. But hopefully we can upload that to like YouTube or something similar soon. How we can see basically how we do this. So we have to go a little bit more simple. We can show you here from the manufacturing sides. We use 2 locations. First one was in Neckarsulm in Germany with our colleagues from Audi, who have basically almost a similar injection molding machine with a vertical press opening, as we do in Wolfsburg. Here in Wolfsburg, we have the Open Hybrid Lab Factory, which is like a research campus. And you can see we have an angle injection molding machine that basically is able to open the mold in a vertical way, so we can actually bring in inserts and bring in these tapes more easily than it would be in a vertical way. If we look into the next slide, of course, then you can see a little bit more detailed the setup, and I'll try to explain it as good as I can. One of the things, of course, we have to do is we have the different layers of the UD tape layup, the consolidated plate. Of course, we have to heat that up. It's thermoplastic to eventually drape it into this nice shape of the tunnel. So we use an infrared oven to place the consolidated plate in, close the oven, heat it up with infrared radiation. Once that's done, we actually have a handling robot with a needle gripper system that is able to transport the layup safely from the oven inside the mold. You can actually, of course, see once you drop it, it almost looks like people always mention it looks like a wet cloth that you just drop over it. And then during the actual processing, then of course we close the mold, which means we compression mold and drape that layup. And then of course, once the mold is closed, we injection mold the injection molding plastic. And of course, we add all these metal components before with an additional robot, or sometimes we did just by hand. And this is basically how we bring these 3 types of materials together. We bring in the consolidated tape layup, we bring in the injection molded plastic, and of course we bring in the metal inserts. And that's of course one of the most important steps here. Very challenging steps here with all these different parameters, with temperatures from the oven side, injection molding machines, the draping, the positions. So very, very interesting process. I hope we can show this video later. I don't know, through YouTube link or something like that. And then of course, we actually after a lot of work and after adjusting all these parameters, we made it to successful prototypes. So as you can see here on the left side in the bottom corner, just to show a little bit where exactly the different materials are, you can see the CAD rendering. But on the right side, the black one, the mostly black component is the one that we actually manufactured. And in this process, of course, we manufacture with quite a variety of parameters, since this is like a research project just to evaluate how the material behaves, how the joining is affected by processing parameters, and basically everything to just evaluate how we can use this technology in large-scale production. And then I'll give it back to Dominic, who's more working on the testing of the components.
Yes, thanks. Yeah, so we received those or manufactured together those components, and as afterwards there are special and many tests required for this project. So first we built up different components and different body in white parts, and also entire body in whites in our development center in Weissach. There are plenty of parameters which have to be figured out in order to integrate this part in an existing body in white structure of a Porsche Boxster. So after this manufacturing process and trials, we also put these components into an oven in order to already simulate the different temperatures for the body in white painting later. As we successfully done these tests, we've been able to insert such a center tunnel in a body in white and bring it to the cathodic dip painting in the production line in Zuffenhausen. So we process and then we also did some crash validation with the single parts and components, and we also some simulations regarding the vehicle testing. So let me take you to the next slide. So this is how it looked like after we finished the part in Weissach. So we had you can see the center tunnel in the body in white. And therefore we used and we investigated also different joining technologies. Blind words which could work with holes in the underfloor. We have delta alpha tolerant rivet, and we also have a plastic friction welding element, which we also could use with the thermoplastic center tunnel and the thermoplastic rib structure at the side of the center tunnel. So, and here's the promised result. So this is how it looked like after we went through the Composite dip painting process. So we've been able to reach this project goal that we could insert it before or like while the manufacturing of the body in white, and then put it or take it through the entire coating process. So this was, I think, a great achievement here, which we could of the thermoplastic material we use because of the special layup and because of the adjusted joining. This is it from my side. So this body in white we sent back to Chris, and probably you will tell us what we done.
All right. Yeah, so one of the topics that we mentioned already in the first few slides was, of course, the joining technologies and all the requirements we have from a vehicle standpoint. Of course, vehicles during their lifetime, especially driving through hot and cold climates, and experience like all these temperature changes that you've experienced on drives through mountains and holidays. But of course, now we have the additional factor that we basically bring a carbon fiber reinforced plastics into a steel frame, basically steel aluminum frame. And so, of course, to basically validate that the joining technologies are valid and are surviving our requirements, we actually went through extensive climate testing. What you can see here is one of the climate chambers that we have at the Open Hybrid Lab factory in Wolfsburg in Germany, and we actually went through an internal test standard to just look at the behavior of the component, see if we see any fractures, and see if we see any deviations. So basically, yes, the testing temperatures are shown on the right. So we have different minutes at different temperatures, ramping up temperatures and cooling down and everything. And we basically used the whole body that we shown before. And actually, you can see here the body has this nice dip coating color, the nice, what do you even call that? Tan color here. And then, of course, one of the things we just, we didn't just put it in, run it through a cycle and just see if it fractured. We actually looked a little bit more into detail and used one of the GOM systems, which is like a visual system to see the deviations in shape and form, to see if we see any deviations or any critical topics inside the component. And we can actually say that we didn't see any critical topics. We passed this test, and actually we are pretty confident with using these type of materials and like a multi mixture of materials inside the car. Of course, at the beginning, especially using carbon fiber, during temperature testing, we were kind of waiting for deformations or waiting for issues with joining technologies, but we actually passed this test very well, and we're very, very happy with the results so far. And so basically now at this point, we're just going to go to the conclusion and next steps. Of course, we've shown with this project, the most important part is really that we can use these type of hybrid components inside the body structure. And I think that's something we really have to stress every time we talk about this, because we've seen composite materials in additions in components that get added to the body after the dip coating process. And of course, materials like this have been very, very, very successful in this section where basically the body gets manufactured, goes into dip coating, and then all these other components get added on. But of course, now we basically enabled this technology to go into body structures, and hopefully from our side, we hope to see a lot more components of this type to go into the body structure and show a little bit more variety of materials inside the body structure. So of course, we showed that it's possible to manufacture these prototypes. We actually learned a lot on the manufacturing techniques, how the material behaves. Of course, the vehicle integration with the the rivets, with the joining technology was an important factor. Also, a lot of lessons learned here. We passed the dip coating process, so that's a very, very important factor in production. If you don't pass the dip coating process in production, that's basically a red flag and cancels these technologies out. And of course, a very, very important factor, which I showed on the last slide, was the climate testing. So we can actually show that these type of materials, that this technology is actually very, very suitable for lightweight and complex geometries in the body structure. And then, of course, we're all wondering what's happening next. Of course, for us, we're going to transfer this to development stages. So now, after showing and proving to our management and to our technical staff that we can do something like this, we had a lot of very, very interesting discussions on further components. Of course, we use this component as like the first component, but we have all sorts of departments that are looking into the body structures and different sections of the body structures where we can use this. Of course, on the same side, we've seen some issues that we want to improve. When it comes to these stages, of course, cost reduction is an important factor. And basically all aspects have shown some, benefits, but also some things we want to improve in the future. So that's something we were working on, and also that's something that we're talking with everybody in the industry who's part of the material itself, who's part of the joining technologies, to see, the things we saw during the project and discuss how we can improve that in the future. And so basically that's the end of our presentation. So thank you very much for attending this presentation. And again, especially here in this project, this has not been only a project with Volkswagen and Porsche. We had all our partners here who are supporting us. There's also a number of partners that we didn't mention on this slide. There's a lot of people from the material side, from the joining side, a lot of companies that supported us through this journey. And we really want to say thank you for everything you did. I think I've seen 1 or 2 or 3 people in the guest list on the side. So again, thank you very much for everything. And of course, one of the important things that we want to say is this has been a publicly funded project by the Federal Ministry for Economic Affairs in Germany. So we got a substantial amount of funding for this. So of course, we also want to thank the German government for supporting us in this endeavor. And of course, also for the TÜV Rheinland, which supported us as a partner. So yeah, thanks again. And I'll give it back to you, Dale.
Thanks, Christoph. Thank you, Dominic. Every good presentation raises lots of good questions. And so, but given the time constraints we've had, I'd appreciate if you guys would go to the chat and try to answer some of those. And then maybe we'll get to a couple of them at the end if we still have time, but we need to move on in the program. So again, thank you. Thank you for your presentation. Certainly very interesting technology.
Yep, thank you.
Yeah, so thank you.
So our final OEM speaker today, as we've moved from the UK to Germany and we come right back to France, is Gérard Liot. Gérard is the expert leader on polymers at the Renault Group. He graduated from the École Centrale de Lyon, especially in material science. Was supplemented by a PhD also at the École Centrale de Lyon with Michelin on fretting wear of tire carcasses. He then completed a postdoctorate at the University of Uppsala Technicum in Sweden on the wear of camshafts for the Renault Group. He's had a number of positions at Renault, and his main activities are to define and implement the strategy and economic technical policy dealing with polymeric materials. For that, he's supported by a network of experts and specialists within the Renault Group and Nissan Mitsubishi. Gérard, welcome to the stage, and we look forward to your presentation.
Thank you very much for your kind introduction. So my presentation will not be as technical as the previous one. I deeply apologize for that. And of course, I do not have the pretension to explain to you what kind of material are the right material for the right places or for the right application in the automotive industry. However, I will try to implement or to put in your heads what kind of question we may have if we do want to increase the use of composite material in cars or automotive industry. We have not to forget the final goal, which is to reduce the carbon dioxide emissions. as you may know, as you already know, transportation are responsible of about, let's say, 14% of carbon dioxide emission worldwide. So it means that transportation are part of the problem, and therefore transportation has to be a part of the solution. And for that, we have different activities in order to reduce the carbon dioxide emission. It could be to reduce the aerodynamic behavior, to reduce the road resistance, to put and create and design some more efficient powertrain, or to use more and more some electrical solutions. And of course, and at last but not the least, to reduce the weight of the different material introduced and used in our cars. We have to reduce the weight for many different reasons. The first one is, of course, the more material you use, the more carbon dioxide you emit during the production of the materials and also during the production of the cars. The more material you use, the more energy you use, so the more carbon dioxide emission you have. And of course, at the end of the day, if your car is too heavy, the drivability of the car is not so nice. So we have in mind lots of different composite materials and application in many different cars. It could be in the bumpers, it could be in the tailgates, in the hood, in the chassis, in the floor, spare wheel trays, or it could be also some trays that you have inside the pickup. And often when we do think about using some composite material, we immediately think that we have to use this kind of material in order to reduce the weight of the car. Weight is important, as I said, and of course tomorrow the car will use more and more lighter components, even in some mechanical applications. So we have seen that, for example, with the presentation of Ford previously. And we have to use this lighter solution in order to compensate the new added functionalities induced by electrification, induced by new gasoline, induced by connected cars or autonomous driving. So let's say that if you follow me, you think that we can use some composite material only for lightweight. Composite material are very important for lightweight, but let's say that sometimes composite material are the right material, the good solution, even for cost. We all know that for small volumes, composite solution could be cheaper than steel solution. So you can see on the very basic and simple example that you have on the slide, after a huge number of parts, let's say after 600,000 parts, the steel solutions are cheaper than the SMC filled with glass fibers. However, for small volumes, the SMC solution is cheaper than the steel solution, and mostly due to the tooling cost. However, with this same example, if we do use some carbon fiber, SMC carbon fiber, the amount of car with which it is cheaper to use some composite material is less or smaller than the amount of car when you are using some SMC with glass fiber. In this case, it's only maybe 50,000 cars. So that's why we have to keep on working in order to reduce the cost, and mostly the cost of the carbon fiber reinforced polymers. So for this, for example, we have used this kind of technology for the Megane Trophy. Composite material were not used only for lightweight, for the hood, but it was also used for the style and for the cost. For this mold production, it was not cheap, but it was cheaper to use some composite material instead of using aluminum or steel. However, as I said, we have to reduce the cost of the raw material. So that's why Renault is working and involved in a French program called FORCE. And the aim of this project is to produce some carbon fiber, cheaper carbon fiber, using the cellulose as a precursor instead of the pan. And we want to achieve 8 euros per kilo for the carbon fiber in order to implement this kind of technology in large volumes. If you are an engineer, sometimes you design the part only for stiffness. But composite material for stiffness is maybe not the good solution, because due to the non-isotropy of material, concerning the value or of the young modulus of the material, often it's difficult for the composite solution to compete with metal like steel or even aluminum. So you have to increase the thickness, you have to put some ribs, you have to find some design in order to compensate and to have a part which is as rigid as the metallic solution. But sometimes it's not possible, and mostly in some parts of the body in white. You may also design the part for the mechanical resistance. And in this case, composite material may or seem to be the right material for the right application. Because in this case, for hydrogen tanks, for example, or high pressure tanks, or even beam for the front part of the car, the mechanical resistance of the composite material lead to a solution which is lighter than the metallic solution like steel or aluminum. Same philosophy for crash absorption. Composite material are the correct material for crash behavior, and the composite energy absorption of composite material are much better than the metal, steel, or even aluminum. So that's why we are planning to use this kind of solution for the crash boxes of our cars, lateral one or front one. And concerning the fatigue, let's say that the mechanical properties of the fatigue of the composite material are very good compared to the steel and aluminum property. So that's why we have validated some application for using some composite spring for our cars. And we are thinking about implementing this kind of application in the future, because the balance between composite and metal is quite in the advantage of composite material. Sometimes when we do speak about composites, the first question we have is, do you have a process which is able to produce a high volume, high number of parts per day? I would say that the answer is quite obvious right now. If you do speak about SMC non-aesthetic application, we have implemented this kind of technology in our cars. We use some SMC materials in our spare wheel trays, and we can produce, let's say, 2 parts per minute with our facilities and the facilities of our suppliers. However, if we do speak about the Class A surfaces, RTM or SMC composite, right now we are not able to produce this kind of technology or this kind of part at a high volume, because at the end of the process we have to polish a lot, which makes the part more expensive and which reduces drastically the cycle time. So in order also to investigate if we can use some composite material like thermoplastic organosheet, we were involved in a project with some French technical institute in order to make some platform with which we are able to produce some parts. In this case, we are speaking about the thermoplastic organosheet, which are stamped, and the cycle time is less than 1 minute. And the size of the part is a little bit less than 1 square meter. So we can say that right now we have the technology in order to implement with a high volume, high capacity, this kind of technology for, let's say, the floors, for example. We did the same with the CRTM technology. We have created 2 platforms, Fast RTM and Fast Form, in order to produce some preforms and to use the RTM process at a high volume. And we were able at the end of the project to produce 1 part with a cycle time of less than 2 minutes. So right now we can say that we are able now, or we are confident in the SMC technology, in the thermostamping technology, in the CRTM technology, and we are confident that we can use them right now in our cars. As a conclusion, because I have to be fast, you have to think that composite solutions are the right material for lightweight, but not always, or not only. Composite material are also a good solution for cost if the amount or the volume of parts that you have to produce is quite low. So in order to implement composite material in large volume, we have first to reduce the cost of the raw material. So that's why we do work in this kind of program like FORCE. We have to solve the class A results or technology. So we must now be able to produce some parts net shape one shot class A surfaces for the body in white application. And obviously, we have also to convince our engineers that this kind of technology are for the raw material, for the product and the process validated and now able for the use in our automotive industry. Thank you very much for your attention.
And I like seeing those photos because I have seen some of those processes in Nantes and as well as in Saint-Avold, and looking forward to hopefully next year getting back to France and seeing some more. I'd like all of our presenters to come back on the stage. We have a few minutes for questions and answer. So Christophe, Dominique, Alice, and Eric, if all of you can come back on stage, I would appreciate it. For Christophe, just a moment. So we have about 4 or 5 minutes here, but one of the things that I noticed that's kind of a common theme today is the use of hybrid structures, whether that's hybrids of continuous and discontinuous composites, or it's hybrids of metal and composites. It's pretty clear that that this has come a long way. What do you think are the big issues with hybrid structures? What do we got to make sure we're watching out for when we think about hybrid structures?
Who wants to go first? I'd say experience, prediction, and simulation.
Mm-hmm. Yeah, Gerard, are you able to join again? I hope you are.
Yes, I'm here.
Okay.
Don't worry.
Okay, we don't see your video. That's what. Maybe it's here. Okay. The other question, I have, and I would like all of you to kind of take a crack at this, is that when we were last together in Paris 2 years ago, the world was all about lightweighting of combustion engine vehicles, and in that short time, and I think it's been accentuated by the pandemic, it's now all about electric vehicles. And so a lot of these solutions were developed around standard internal combustion engine vehicles. Where do you see the best applications in the next generation of electric vehicles for these kinds of structures?
I'd like to take that one step further, if possible, Dale. I think actually when we're looking at hydrogen vehicles, when you're looking at pressure vessels, as I think was on some previous slides, really the best material that we can have due to the pressures and the requirements that we have for those components will be looking at composite materials. So I think that'd be a real game changer in terms of using composite materials in more high volume vehicles.
Sure, the pressure tanks, of course. Yeah. Okay.
I do think that even if lightweight could seem to be less important because we are using some electrical cars, because of course when you are using some electrical car during the use phase you are not emitting any carbon dioxide. So you may think that light or weight is not that important or as important as before. But as we said, or as I said, weight or the total weight of the car is very important because for the drivability and, for example, you do not want to drive a Panzer or tank on the road. You may have some problem with your driving license. And of course, we have now sometimes two engines in the PHEV. You have the thermal engine, you have the electrical engine, you have the fuel tank, you have the battery. So you have to reduce somehow some other parts, to reduce the weight of some other parts in order to have at the end a normal European car, just to make sure that the normal driver could use them. And of course, the more material you are using, the more energy you are consuming, the more carbon dioxide emission you are emitting. So it's important to maintain as a normal or acceptable level the weight of the car. So if you implement, for example, some hydrogen system inside the car, it means that someone somehow has to reduce the weight of some parts, the tailgates, the hoods, the doors, or whatever. So weight is still important even if we use some thermal engines. So
And also
composite
for the
is a good solution.
And also I would add it for the EVs because they're also for the range of how we can get with
Yes.
the EVs. They're also the lightweight is and will be an important factor in the next couple of years.
Okay.
In fact, if you reduce the weight of some parts, the battery will take the place.
Yeah, it just creates more space for more batteries. Of course, and of course that extends range. Yes. Okay. Okay, good. We've reached the end of our allotted time. Again, I want to thank all of our speakers. It's been an excellent series of presentations, an excellent session. Again, thanks to all of you, and thanks to all of you for attending. This automotive session, the next episode or next event on the JEC Connect today is the Startup Booster. That starts at 5 p.m. Central European Time, 4 o'clock for you, Alice, and then 11 a.m. for us here in the U.S. On the East Coast of the U.S. So, thank you again for joining us, and we'll see you in a handful of minutes.
All right. Thank you, everybody.
Yeah,
Bye.
thank you, everybody.
Thanks, everyone.
Bye.